Welcome to a massive open online course on fluidization engineering. So, today's lecture will be on attrition in fluidized bed. I think we have discussed about that particle alliteration and entrainment in fluidized bed in the previous last two lectures, and there we have also discussed the mechanism of entrainment and how these entrainment characteristics can be modeled, and also alliteration, how it if it is affected by different particle size, and also attrition mechanism there. So, in this lecture we will be discussing about the attrition of the particles when those particles will be interacting during the operation of the fluidization. So, there may be due to this attrition the particles will be broken up into a smaller one, and then entrainment of these particles will be happening there. And also this attrition may be depending on the particle characteristics, event size distribution, etc., in the fluidized bed. So, we will discuss about this here. So, before going to details of this attrition, we should know what is the definition of attrition, and also how this attrition can be expressed mathematically there. You know that what is the attrition. Basically, if you are going if you are saying about that attrition, it will be just generation of fine particle by acceleration and collision near the tip of the gas jet that is promoted from the nozzle of the gas distributor, which is called the particle attrition. So, actually basically this is nothing but the generation of fine particles by collision of the particles. And this attrition rate, that is overall attrition rate, is defined by the relative change of the bed mass, or by the relative change in alliterated mass of fines, which are mathematically expressed as follows here. Now, here this R A 0 is the overall attrition rate, and W bed and W E I or E L, you can say that are the masses of bed and alliterated fines respectively. So, R A 0 is being represented by this here as 1 by W bed into rate of that means weight of fine beds here in the fluidized bed per unit time, or this can be represented by this alliterated fines, rate of alliterated fines formation, that is 1 by W bed. This is the weight of the bed of solids there, and this d W E L means here what will be the weight of alliterated fines that is generated by the collision of particles per unit time here. So, this will be your rate. So, this is in this way that the mathematical expression of the overall attrition rate can be given here. And what is the importance to know the attrition mechanism, and why attrition characteristics to be actually required to study for this. The attrition of the particles, actually it is a serious problem which widely occurs during the processing and handling of particle solids in chemical, even agricultural or in allied industries. So, attrition has deleterious effect on the product quality and on the reliable operation of process equipment, because of that some changes in particle properties, such as like particle size distribution, shape and surface area, which will govern the change of mass transfer or heat transfer characteristics in the fluidized bed. Even if is there any loss of the fines during the operation of the fluid operation, then how much fines is formed by the attrition or by that elucidated fines, how they are coming out, what will be the mechanism for that. Of course, you should know, because all those things to be taken care of whenever you are operating fluidized bed with some catalyst particles for the specific application, because some loss of particles may hinder the performance of the fluidized bed. Even somewhere you will see, if some operations is well defined or well characterized by the fine particles, whereas if you are having the coarser particles, then you have to know how much coarser particles will be there, how much fine particles will be there inside the bed. Then based on which you will have to actually judge that what will be the performance of the fluidized bed there. Because this is very important, because what will be the amount of fine particles is coming out from the bed, that is, I think we have discussed in the previous classes, that what will be the exit entrainment rate there, and this is coming because of that attrition. Not only attrition, after attrition there will be some mechanism of that ejection of the fines by the bubbles whenever it will be dissolving the surface of the fluidized bed. Now, in this case, of course, that is why you have to know some extent of the characteristics of the attrition inside the bed. And overall, the problems associated with the particle attrition have significant cost implications in process industries, of course. And for well design of the fluidized bed, it is necessary to know the attrition characteristics of materials and the breaking energy supplied by the system, and the distribution of the attrition rates among the particles also you have to know before going to design the fluidized bed. And knowing the particle population also is essential in the judgment of the bed performance and the particle entrainment or elucidation inside the bed. So, we have to actually know something about that attrition characteristics inside the bed, because of which. Now, what should be the mechanism of this attrition? You will see this mechanism can broadly be classified as one called surface wear, another is called fragmentation. Now, what is surface wear? Surface wear may be two types, abrasion and the erosion. So, attrition mechanism of particles that depends on the particle strength and the breaking force, the breaking of the material can change from abrasion to fragmentation, or you can say that splitting with increasing breaking force. And with the same breaking force, you will see that splitting may occur for a weak, but not for a strong material there. So, material property is very important here, whether this the particles will be attrition will be there or not, because if the higher strength particles may not be very easy to broken up into a finer ones. So, there may be some, even sometimes you know that in wet solids may not be easier to broken into finer particles there, because of some abrasion or adhesive nature of the particles inside the bed here. No. So, in this case these two mechanisms are there, one is called abrasion. Here see one particles just breaking into one and then another finer particles almost uniform in size, whereas these particles may be broken into fragmented solids. Now, the size of the solids may not be equal in size there. So, the distribution of the solids after attrition, you will see two types of distribution will be having based on these two types of mechanism of attrition there. After abrasion, you will see initial here, after abrasion this type of mechanism, this type of distribution is coming here. So, initial distribution is like dotted line is represented by initial distribution of the solid particles inside the bed, whereas after attrition you will see the distribution how it will be changing because of formation of fines there inside the bed. Again for the fragmentation, as per fragmentation here, how sees this after attrition how it will be changing this you will see that a variation of this distribution will be changing because of the attrition. So, this is the distribution of the initial distribution, means that you are putting the catalyst particles or some other particles, maybe inert particles, that is not taking part into the reactor for reaction or any other physical operation that may be. So, those mixture will be having some certain distribution. So, initially this distribution will be like this, and after that you will see that after fragmentation it will be distributed with wide spreading like this type of. Whereas, in the case of abrasion there may not be that much of spreading of that particles after abrasion here. So, this mechanisms actually will be having that quantify the attrition extent of attrition based on this distribution function after attrition. Now, this attrition depends on what? Basically, whether these particles are in very strength, or that is depends on the properties of the particles, whether particles are very strong or it may broken into fine particles very easily with a very small force also you can say, and the breaking of the material can change from that abrasion to that fragmentation, that is two natures just because of this their particle properties, or it may split with the increasing breaking force there. And with the same breaking force you will see that splitting may occur for a weak or not for a strong material there. And what is that fragmentation? Fragmentation is nothing but a process where a particle splits into several smaller particles by the propagation of the radial or median cracks. In principle, this fragmentation is the large scale fracture, whether the cracks are generated in the area with high level of stresses, and you can say the develop this will develop through the whole volume of the particle. Now, fragmentation may be dominant mechanism of that contribution of the attrition process, and in that case although in some circumstances it can occur in attrition of bulk solids such as in shear deformations, and particles of intermediate size may result from the fragmentation and that may be very rare in case, but there may be possibility of that particles of intermediate size resulting from that fragmentation. So, we can say that this fragmentation is nothing but the splits into several smaller parts of that particle by the propagation of radial or median cracks. And what is that? And this is being developed to the whole volume of the particles here, and this may be the dominant in that nature compared to that abrasion mechanism. And what is that surface wear? Surface wear is the surface damage of particles here. Here surface is being damaged. It can be subdivided into abrasion and erosion. Now, abrasive wear is due to the action of particles, that is being slides or you can say roll over each other, whereas erosive wear that may result from the particle collision. So, we can say that this abrasive wear is nothing but the action of particles sliding or rolling over to each other, and whereas erosive wear, this is two types of wear, surface wear are there. So, erosive wear results from the particle collisions, and maybe you will see that material removal will be happens due to this surface damage in semi brittle failure mode, and which is attributed to the formation of substance in lateral cracks. And this process is commonly referred to as chipping, which is the actually mechanism of impact attrition of the particulate solids. And by abrasion, very fine particles that are produced leads to bimodal particle size distribution there. And because of that abrasive attrition, a mother particle, or you can say that this initial particle is disintegrated into two parts, and one is the fines and another is single Son particles there, which is only slightly smaller than the mother particles. And the extent of this abrasion that is related to the fragmentation depends on the density, mass density, you can say mass density distribution of the particles. So you can observe or you can identify what should be the extent of abrasion relative to the fragmentation based on the mass size distribution of the particles there. So, we are having the two types of mechanism here, one is fragmentation, another is surface wear, whereas surface wear have two types, there is abrasive wear, another is called erosive wear, whereas abrasive wear is resulting from the action of particles by sliding or rolling over, and erosive wear, that is results from the particle collision. Even fragmentation also, it is being formed by the particle collision also, but there the formation, that is size distribution, will be different there. And this process generally sometimes referred to as sipping of the material simple. And in general cases, you observe that by this surface wear mechanism, whenever smaller fine particles will be formed, the distribution of that daughter particles will be bimodal in size. So, we have to know that okay, if it is that size distribution like this for this surface wear and such distribution from this fragmentation, what should be the difference from which you can say you can identify what extent of actually attrition happens inside the fluidized bed. Now, before going to the actually mechanism how this happens, you have to know some extent of that theories on that. What is the mechanism, what is the theory behind it, that okay, particle is collision and then it will form the smaller particles. Generally, three fundamental, you will see that comminution theories that are used to correlate the degree of size reduction with the energy consumed. That so, the formation of the fine particles, that depends on the how much energy is consumed for this splitting of the particles or breaking of the particles into fine one. So, this degree of that size reduction, you can see that formation of fine particles, that depends on the energy consumption. There are generally three general formula that is given by different investigators like Rittingers and Keek and then Bond. There are three fundamentals theory by which you can explain how this actually this comminution of the particles is happened inside the bed. So, Rittinger's surface theory, as per that that the energy consumed is, that is proportional to the area of that new surface formed during this attrition process. And as per Keek's volume theory, that the energy required to bring this analogous changes in the configuration of geometrically similar bodies of equal you can say technological character is proportional to the volume of these bodies here. And as per Bond's theory, that you can say that the energy required for this breaking up into finer ones is proportional to the length of the crack that is initiating for this breakage to form or to result the fine particles there. So, there are these three theories, all those theories actually basically based on the energy consumption. Now, after breaking, what will be the size, what will be the volume of the bodies that is formed, and also what should be the length of the crack, that depends based on who is that these three separate or different theories are given or explained or proposed by these investigators. Now, general equation of comminution that you can say each of the three well known theory of the comminution can be represented in the special case of general equation like derived by Ouwerkerk et al. 1937 here. So, they have explained these theories like this dE, that means here net energy changed, that will be is equal to proportional to the what is that dx by x to the power n here. So, where E is called the net energy for unit weight of the material in a particular comminution process, and x is a factor here that indicates the fineness of the material here, fineness, that is what extent of fine particles are being formed inside the bed. And here exponent that is called n is the factor indicating the order of the process there, and C is an constant that can be obtained by the experimental, which depends on the material properties and also other physical operating conditions. And the exponent n is or you can replace this exponent n by numerical values of 2, 1 and 3 by 2, the integrated form of the general equation that is leads to the well known fundamental theories of Rittinger's, Keek and Bond respectively. So, if you replace this n by 2, that will be actually as per the equation of Rittinger's or theory of Rittinger's, and if you substitute this value of 1, then it will be simple Keek's theory, and if you substitute n is equal to 3 by 2, it may be expressed or it can be referred to that Bond theory. Now, net energy to bring about this size reduction, what should be the net energy that is to reduce the size of the particle inside the bed. So, for all practical purposes, you can say this measurement of the net energy to bring about this reduction of this size of the particles to the desired product size, that is very crucial to know here. The corresponding net energies per unit or you can say per unit ton required for the feed x 1 to the product x 2 here. So, if you are expressing that product size is x 1 here and product size is x 2 and the initial size is x 1, then x 1 to x 2, to reduce this x 1 to x 2, what should be the amount of energy required per 1 ton, that can be expressed here as per Rittinger's theory. It will be equal to E is equal to C into 1 by x 2 minus 1 by x 1. As per Keek's theory, you can express this energy consumption as E will be equal to minus ln, that is logarithm of, that is ratio of final product to the initial size. Now, here as per Bond's theory, you can say that this energy consumption will be equal to 2 times of C into 1 by root over x 2 minus 1 by root over x 1. So, these three equation you can use how much energy will be consumed if you know that initial and final size of the particles. Now, experimentally how to obtain this extent of this attrition here. So, the test methods can be classified into categories such as multi-particle and then single particle test here. If you are using different types of particles, maybe coal and with sand mixture, or maybe similar type of particles, their collision will be there, maybe 2 types of particles. So, that is why multi-particle or the single particle will be there. So, if you are doing the test with multi-particle, then of course, you will get different types of actually different characteristics there. So, in case of multi-particle tests, there you will see it is called grinding mill test here. So, it is generally described by the grindability index, which sometimes it is called hard group index there, AGI. This AGI is based on the quantity of new surface that is created during a specific grinding process that on a closely sized sample of materials there. The Rittinger's model generally is used to calculate the extent of this new surface produced. The value of this hard group index is presented as a percentage of new that is generated surface by comparing with that of a standard coal sample there. And hard group index describes a relative propensity of the attrition only there. So, hard group index can be represented by this here. This is AGI, that will be equal to 1 3, that means 13 plus 6.93 into D, and this that means here D is the factor here. 50 gram of air if you dried coal featuring a grain size in the range between 0.6 and 1.2 millimeter are filled into the sample mill, and a weight is put on the mill's grinding stone. After 60 rounds, the grinded coal is put on a sampling sheave. Factor D equals the fraction of the coal that is passing through the sheave. So, if you are able to, after grinding, if you pass it to the sheave, then what should be the fraction of the coal that is passing through the sheave? If you represent it by D, then hard group index will be equal to 13 plus 6.93 into this fraction of coal passing through the sheave here. As per shear cell test, this test is used to study the attrition resulting from bulk change of particles as they are subjected to sliding in a closely packed bed there. And multi-particle tests are closer to the real process, but to assess the relative you can say attritability of a particular material in a specified testing device. It has some disadvantages such as in the multi-particle test that do not account the influence of physical phenomena and the mechanical properties of the material that are being attrition that are being used for attrition. The mechanics of particle interaction in both the test actually devices and the real process is not sufficiently well understood to maintain the dynamic similarity inside the test devices. So, generally you can do that shear cell test, but you may not be getting the exact results because of this some shortcomings of the device that you are being used. And experimental techniques for the single particle test, you will see that single particle test in contrast you can say allow well defined and controlled loading to be applied to a single particle there. And therefore, you can say that entrance or you can say that the understanding of the particle breakdown is very easier by this single particle test. And techniques for single particle testing, here there are several techniques, of course, mainly two techniques are being used for this testing. One is quasi static indentation techniques, that is used as a tool for modeling the conditions of local that is contact such as that occurring during the attrition. and compression between two platens that is relevant to the crashing of bulk particles, where the the failure that is dominated by fragmentation, and you can say striking of the particles that against a rigid flat target at a required velocity in that case, and may be often achieved by the use of compressed air. So, these two techniques are being used for single particle test here, because that here in this case the local contract such that during that attrition will be actually obtained by some mathematical simulation. And also you can say that sometimes bulk particles that are failure, which will be dominated by the fragmentation, and then you can obtain by that compression of the two platens by this compressing air. So, these tests may be related to the process where attrition occurs by the velocity, and interparticle and particle wall impacts such as in cyclone or centrifugal device, and then jet region of the fluidized bed and pneumatic conveyors. You will see that attrition basically it is predominant in the region of that distributor, where the gas jet is coming from the distributor, from the hole distributor hole there. You will see that the velocity of the jet will be very higher, and if your hole size is very low and gas velocity so high, in that case you will get the high jet, and because of that high jet the particles particle interaction and also the collision between the particles will be higher, and because of which there will be the attrition. So, this attrition actually depends on that energy related, and also there will be some wall effect. Of course, if there is the particles of that is smooth surface, then attrition will be less compared to that. If surface of the particles would be that is not in smooth, that is rough surface, then attrition will be more there, because the attraction because of that collision and also that interparticle, that is heating of the surface will be more intensive than the regular surface. Now, you have to evaluate the attrition after this testing, and you can say that attrition after attrition process, you have to evaluate what will be the actually overall attrition rate in the process. So, the overall attrition rate is defined by the relative change of the mass, or by the relative change in electroated mass of fines, which are mathematically expressed as follows here. So, this already we have given earlier also. This R A 0 is the rate, overall attrition rate, and that will be equal to 1 by W bed into d W bed by d t. So, or by this equation you can this. So, R A 0 is the overall attrition rate, and W bed and W E L are the masses of the bed and the electroated fines that is being formed after attrition. Now, choosing of these equations that depends on the type of equipment also that are being used for the fluidization. So, as per Guin 1969, that the degradation of the catalyst in a small scale test apparatus they have done, as they are actually observation, the electroated particles can be considered as the attrition product, and the increase of the electroated mass, that is W E L, with time by an equation based on the initial solid based mass, that is W bed 0, which is known as Guin equation here. Guin equation, this as per that as per his actually suggestion or proposal, that the attrition rate can be expressed in that way. This W E L by W bed 0, that will be equal to K A into T to the power B here. Now, the variable T here is called the shearing time of the particles. How long this particles will take part for the shearing with other particles there. And the attrition constant, this Ka actually is the constant that will be obtained by experimentally, and this decreases with the mean particle size also. If the mean particle size is smaller, then you will see that this K value also will be decreased. So, in that case the exponent B is constant here in this case. So, actually basically this K value and this B will be obtained from the experimental results. And we are Ouwerkerk 1991 and Kelleher 1992 model. As per their model, they suggested that the attrition rate that will be vary with the applied normal stress and the shear strain in a way that could be expressed by the following formula here. Here WEIL is nothing but the alliterated mass of the fines that is formed by attrition, and K is the constants, alpha is also a constant. Here this gamma is one factor that is called shear strain. This is effective shear strain. So, this will be as per defined by this theta by 360 into 2 pi r bar by h into f, where theta is the rotational angle in that device of that test in which this attrition test is being done, and h is the effective sample layer thickness also, and r is the mean radius of the shear cell in which this test is being done, and f is the slip factor which is equal to 0.86. So, after substitution of this value here during the experiment, you will get this shear strain. Once you know that shear strain, and then what is the shear this normal stress, this sigma sigma here reference is called a reference normal stress, at which the amount of attrition product is the same for all types of material that is being to be tested. And here alpha and Ka to be experimentally obtained after substituting those parameters here in this equation. Ghadiri et al. 2002, they have actually proposed another model actually based on this proposal of Neil and Bridgewater 1994. So, Neil and Bridgewater 1994, they have proposed that the rate of attrition should be related to the sigma into gamma to the power phi, where phi is an exponent which only depends on the material type. So, this one, and based on this concept, so Ghadiri et al. 2000s, they developed a correlation by fitting their experimental data like this here WEIL, that will be equal to 3.858 into sigma gamma to the power 0.5 to the power 1.053. So, these exponents, these constants, they got it from their experimental results. So, here this phi is nothing but that here 0.5 here, whereas this other exponents that this proportionality constants will be equal to 3.858. So, basically from this correlation you also be able to calculate what should be the allotable mass of fines that are formed after attrition process. Once you know this this normal stress and the shear strain during the process. Zenz and Kelleher 1980, they also proposed some correlation to interpret the attrition rate inside the fluidized bed. So, based on their fluidized bed experiment, different investigators also assessed the attrition rate in different ways based on the examination of a group of particles. For FCC catalyst and glass beads, Zenz and Kelleher developed a correlation for the attrition rate without without using any shroud for upwardly directed jet which is coming out from the distributor hole, and based on their experimental data or their concept, they have proposed this correlation, that is phi dashed, that is called flux of attrition per unit hole through which this gas is coming out, and K A into U O R to the power root over G O R 2.5. Here K A is the attrition rate constant that depends on the particle diameter. U O R is nothing but the velocity of the gas which is coming out from the orifice, and this rho G O R means here density of the gas or fluid at that orifice location, because due to that higher jet, and there will be some change of temperature because of this collision or because of the friction of these two particles, and there will be change of temperature instantly, and then there will be change of density of the gas. So, at that orifice hole, what should be the temperature, and based on which what should be the density of the gas there. So, that depends on this attrition rate. That attrition rate depends on that density of the gas here. So, here and this attrition rate per unit hole, that is flux is based on the cross sectional area of the nozzle, you can also define that way. So, that is kg per minute per hole per unit cross section of the nozzle. So, in that way you can calculate. So, this K A, that is attrition rate constant that depends on the particle diameter, you will see that 0 to 2 micrometer particle diameter, this attrition rate constant will be equal to 1.11 into 10 to the power minus 6 as per their experimental data, and 0 to 23 micrometer diameter, their attrition test gives their 9.03 into 10 to the power minus 6, and for 0 to 50 diameter, this attrition rate will be 22.29 into 10 to the power minus 6. So, in 10 to the power minus 6 range, here the rate constants will be obtained. So, this is the typical values they have obtained from their experimental data. And so, after just substituting this K value, and if you know that orifice velocity and the density of the gas, then you can easily say what should be the flux of the attrition rate, flux of the attrition per unit hole that can be obtained from this equation 12. Now, what is the extent of attrition? Extent of attrition means the time integral of the attrition rate, which is expressed as this R A Ex for extent, which is that is depending on time. So, as a function of time, it will be 0 to 1 into R A T dt. The extent of attrition depends on the initial breakage and initial fines content in the bed. Modeling of attrition, you have to do some modeling, you have to develop some model in such a way that you can predict predict the attrition rate inside the bed. There are generally three sources, those are contributing to the attrition of the fluidized bed system. One is jet-induced attrition model, another is bubble-induced attrition model, and then cyclone-driven attrition model. Jet-induced attrition model occurs generally at a certain volume above the gas distributor, which is defined by the jet penetration length. And bubble-induced attrition model generally caused from the low velocity interparticle collisions. And cyclone-driven attrition model is generally expressed by the forces that is exerted by the cyclone on the particles. And jet-induced attrition model occurs at a certain volume above the gas distributor, which is defined by the jet penetration length. And there are various variables, of course, namely nozzle diameter, number of orifice holes, even gas flow rate, and then gas velocity, orifice velocity, gas density, and all other parameters. Sometimes you will see that even size of the particles also the effect the attrition in the jetting region. If there is no interaction between the individual jets that is coming out from the hole of the distributor, the entire rate of attrition in the jet region can be obtained by summing the contribution to that of each jet. If suppose there are 3 jets that is used for the fluidization to distribute the gas through this jet and through this hole as a jet. So, if individual jet is giving their individual contribution for the attrition rate, then you have to summing up. If there is no actually interaction among the jet, if there is a you can say that interaction between the individual jets, then there will be attrition rate may be will be changed because of that the collision rate and also the efficiency of the breakup of the particles there in the distribution region. And also sometimes you will see if the interaction of the jet is there, the energy which is coming out from that hole as a gas jet there. So, it may be sometimes change that energy distribution in the fluidized region, that is distributed region, and because of which the attrition rate will be changing. Now, the overall attrition rate you cannot of course obtain what that is there any interaction or not. It is very difficult to measure that whether interaction of the jet or not, and it is not possible to measure also in that particular dynamic condition. So, overall attrition rate to be obtained after just getting what should be the fine formation is there. So, the overall attrition rate of the region above the distributor can be defined by this R A distributor, that will be equal to NOR into RAG. Here NOR is the number of orifice hole in the distributor, and RAJ is the rate of attrition for this jet. This RAJ is proportional to this gas density and the square of the what is that, or you can say that cross sectional area of the orifice hole, and also what should be the flow rate of the gas through the orifice hole. And this proportionality factor depends on the properties of the solid material. The attrition rate per jet, this RAJ is proportional to the square of the orifice diameter, and the jet velocity is one of the decisive factor you can say for the jet induced attrition. The extent of the attrition that depends on the jet gas velocity that is raised top power of n, where n varies between 1 and 5.1. So, in this way you can calculate or predict or interpret what should be the overall attrition rate of the region above the distributor there. Only thing that you have to know what will be the number of holes is there, and also RAJ. This RAJ you can get this what will be the fine formation, and then at the different operating condition, and after fitting this data with the models here, then you will get the proportionality constant. Once you know that proportionality constant, you can say what should be the overall attrition rate of the region above the distributor. Now, as per bubble induced attrition model, you can say this bubble induced or attrition model basically happened because of the low velocity interparticle collisions. The momentum exchange therefore is not that much high to break into the finer particles, and this bubble induced attrition rate is described by the relative production rate of the fine particles here. So, this RABUB means here bubble induced attrition, that will be 1 by W bed into rate of change of this filtration due to this bubble ejection of the solid particles in the bed. Now, W bed is the instantaneous bed mass and W EL bub is the mass of fine particles which is produced by the bubble induced attrition. And the production rate of the bubble induced attrition can be actually obtained by eliminating the jet effects of course, and this can be obtained by using the porous plate distributor for distributor of instead of grid or jet distributor to avoid the grid jets. Basically, the production of the fines by bubble induced attrition that creates new surface area of fine particles. So, in this case you can say what should be the amount of new surface area are formed when fines are formed there during this attrition process, and then from this surface area the rate of surface area that is generated which will be proportional to the rate of energy input for the bubble formation, which is written as this S dot here S dot is nothing but the rate of surface generation which will be directly related to the energy consumed during this bubble induced attrition. The rate of production of this new surface area can be represented by this rate of course that mass rate of the production of the fines as this S dot is equal to R A bub into W bed as per equation 18 here given. So, the total rate of energy input to the fluidized bed for this attrition process then can be expressed as this E total will be equal to volumetric flow rate into pressure drop. You know that pressure drop which are already being actually discussed earlier in the lecture, how to calculate the pressure drop there, and what should be the volumetric flow rate inside the bed. If the volumetric flow rate, if you know the velocity of this gas or fluid, and then if you multiply by cross sectional area, then it will be volumetric flow rate, and then pressure drop you can represent it by this. And if you substitute this here and finally, after simplification you can get the W bed into UHG into Z. This is your the total energy that is being consumed for the attrition process there. And the energy required to keep this particle suspended of course is suspension, that will be equal to U H G M into A bed, and then here this M for your minimum fluidization condition, and then this W bed into Z by A bed, that will be W bed U H G M G. So, this is the energy required to keep the particle just suspended. So, what will be the minimum velocity of the fluid for getting the minimum fluidization, and what will be the energy supplied for this will be called E dot suspension. And the remaining part of the total energy that will be supplied is which will be utilized for the bubble formation there in the bed. Now, thus for bubble induced attrition, which then can be represented as like E bub is equal to what will be this here total energy here, this is called W bed UHG into G, this is called total energy supplied here, minus this is what will be the just energy consumed or supplied for just getting the bed in fluidized condition, or you can say that get the suspension. So, after subtracting you can get this equation for energy supplied for the attrition by this bubble induced mechanism. Therefore, the bubble induced attrition rate can be expressed from the equation 17, 18 and 21 as given, that as per here after simplification you can say this will be equal to K bub into UHG minus UHGM into Z. Here K bub is the proportionality constants which will be obtained from the experimental data here. As the bubble velocity increases, of course, the bubble induced collision between the particles of course will be increases with the bed height. And for this reason Ouwerkerk et al. 1980 proposed another model for bubble induced attrition rate as per here given in equation 23 R A bub, that will be equal to K dust bub into UHG minus UHG into H bed here. Earlier one is here UHG minus UHG into Z here, whereas here it will be H bed as per this height. So, this K Bob dashed is also attrition rate constant as per their Ouwerkerk et al. 1980 model. Kono 1981 found that the attrition rate is exponentially increases with bed height with the exponent of 0.78 here, which is expressed in expressed by this equation given in equation 24 here. And cyclone driven attrition, in this case it is actually happened because of the forces that exerted by the cyclones on the particles, and the forces lead to impacts and rubbing on the inner wall of the cyclones, which results in breakage and attrition phenomena and the change of the particle size distribution. It is possible to quantify the attrition via the mass of fine particles that is being left the cyclone through the overflow as shown in the figure here. So, if you know the mass of fine particles that is leaving the cyclone through the overflow, you can quantify the attrition, and these particles are collected on a filter who itself can be weighted in well defined atmosphere, and particles from the cyclones through the underflow are collected in a hooper, and from this you will be able to calculate what should be the quantity of the attrition via this mass of the fine that is collected. For separate cyclones, or you can say isolated cyclones, the attrition rate is measured as mass flux of the fines loss per unit mass flux of the feed to the cyclone, which is defined by this equation 25. And in the spiral, or you can say tangential cyclones, the particles are accelerated to a vertically which is related to the inlet gas velocity of the cyclone, and the kinetic energy of the solids which is transported per unit time into the cyclone is calculated by this equation 26 here, half of m UC square. And the production of the free surface energy via this cyclone driven or you can say aberration which is contributed by the fraction eta of this kinetic energy supplied to this cyclone here. And the fraction eta is a function of the solid loading in the cyclone, and it follows exponential function here as per equation 27, where here in this case K C L is called the loading constant, and this loading is defined by this m here, then m will be equal to m C in by u C in A C in here. So, C is for cyclone here. So, Riefenhagen and Werther 2000s found that this exponent of n will be negative of 0.5 from their experimental data. And also cyclone driven model, as per that what should be the loss of fines from these cyclones, that can be calculated from this equation here given as 31 eta m c in by 2 gamma into S m u c in square. So, this will be basically depending on the cyclone velocity and the mass of the fines that is collected there. And substituting the equation for m, the equation 31 can be simplified and can be expressed by this equation 33 here. So, this attrition, I think we have learned something about what is the mechanism of that attrition process in the fluidized bed, and how this attrition can be mathematically expressed, and what are the different tests of doing this attrition, and attrition depends on what? Attrition depends on the particle size and also particle size distribution, or also what will be the energy consumption during this attrition, and the theory given by this Rittinger's bond and then Keek based on there is energy consumption for production of the fine particles during this attrition process. And also different models that are defined here. You can use this model for interpretation of this attrition process in the fluidized bed. Also you can predict the attrition process, attrition extent of the attrition inside the bed. And you can generate also your own model by having the different parameters based on their operating condition, doing experiment in the fluidized bed, and also collecting the fines after attrition and measuring it, and then fitting with the experimental fitting with some with your experimental data with some suitable model, or making the model in your from the basic theory you can develop also. So, more about this attrition will be discussed in the next lecture. Okay, for this further reading you can go through this reference here given here. Okay. So, thank you.